Okay, starting with this video then. So I've added a drop of one solution into another solution, and lo and behold I get this yellow precipitate forming. So that's the solid that's falling out of solution here. So that's kind of the topic of this video, solubility, and particularly something known as the solubility product constant, or shortened to KSP. So hopefully you recognize the fact that it's called KSP must be dealing with equilibrium. So let's get started with this. Let's have a look. So here's an example of an equilibrium between a solid and an aqueous solution. So this is actually a silver chloride, AgCl. And so what we have here is, in one direction we have this solid silver chloride being dissolved. So we have AgCl solid yielding aqueous ions, Ag plus Cl minus. But we also have this process here where we have some of this hydrated chloride ion, or hydrated silver ion, forming solid silver chloride. And so we have these opposing reactions. There they are, AgCl yielding Ag plus Cl minus, AgC minus, Ag plus Cl minus yielding AgCl solid. So that is an equilibrium, two opposing reactions. And at some stage, when you have a saturated solution with some solid still present, you have an equilibrium. So that's really what we're talking about here. A few definitions to begin with. Molar solubility. So the molar solubility, amount of compound that would dissolve in a solvent. So this is a maximal concentration of the solute and is usually expressed as moles per liter. It's like a concentration, but it's saturated solution. Okay, that's what we're looking at here. Solubility equilibrium, that is a dynamic equilibrium that exists in a closed system at a given temperature between solute and solvent in a saturated solution. Again, saturated. Solubility product constant, and KSP is the value at a given temperature attained by solving an expression for solubility equilibrium. So it represents an equilibrium that exists between the solid and its dissolved ions. And once again, that's in a saturated solution. So a few definitions to keep your mind on as we go. So let's look at this equilibrium here. For calcium fluoride. So we can write this expression. So again, there I have my calcium fluoride solid. At the bottom I have hydrated calcium ions, hydrated fluoride ions. So one thing we want to do when we're dealing with solubility equilibrium is always write our dissociation expression. So dissociation expression for calcium fluoride solid looks like this. 2F minus. Okay, so don't forget the stoichiometry involved for calcium fluoride. Whoops, I forgot the 2 there. So calcium fluoride, CaF2 yields calcium ions plus 2 fluoride ions. And so you'll notice this is a heterogeneous equilibrium because I have solid state and I have aqueous. So I can now write a KSP expression. And remember, KSP expression, I ignore the solid because the concentration of solid would not change. So I have calcium 2 plus multiplied by F minus squared. And so there's a solubility product equilibrium. So we can, just like we did in previous videos, we can start looking at calculations for this particular equilibrium. Before we get started, let's just have a little bit of practice. So, write a dissociation equation and solubility product expression for the following. So, magnesium sulfide, manganese 2 sulfide. So, Mn2 plus aqueous plus S2 minus aqueous. So there's the dissociation expression for manganese 2 sulfide, and then the equilibrium expression, KSP equals Mn2 plus multiplied by concentration of S2 minus. So there's an equilibrium for that. How about lead 2 phosphate? So equilibrium, dissociation, Pb2 plus times 3, that's what the 3 indicates, plus PO4 3 minus aqueous times 2, that's what the 2 indicates. So there's a dissociation, and a KSP expression for this is going to look like Pb2 plus cubed times phosphate 3 minus squared. So you can see, and this is not necessarily uncommon with KSP, we're dealing with ionic solids, you can end up with some fairly high exponents in your equilibrium expressions. Alright, so 2 calculations that you need to be able to do. First of all, calculate the molar solubility given a KSP. Secondly, well, it's the other way around, calculate a KSP given molar solubility. Remember, molar solubility is basically a concentration in moles per liter referring to the solid. So let's have a look at these. So let's go back to our first example, calculate the molar solubility of a saturated solution of manganese 2 sulfide. 25 degrees Celsius, KSP is given as 3 times 10 to the minus 14. So there's our dissociation equation, and what you can do here is also do an ice table. Now you'll see these ice tables are pretty simple, and you won't necessarily have to follow them through too far. But let's do one anyway. So what we're looking for is concentrations of these 2 ions. That's what's going to give us the molar solubility. And so we know before we add any solid to the liquid, the concentration is 0. The change is going to be plus X for manganese and plus X for the sulfide ion. So X and X. And so once we have our ice table, we can plug it into a KSP expression. So there's the KSP expression we wrote out before. And we're just solving for X. So KSP 3 times 10 to the minus 14 equals X times X, or X squared. So in this case, X equals 2 times 10 to the minus 7. And that is the molar concentrate, or molar solubility. So X is the molar solubility in moles per liter. 2 times 10 to the minus 7 moles per liter. Don't forget to write that constant moles per liter for molar solubility. So calculating molar solubility is pretty straightforward. You just solve for X and you get a single value of X, molar solubility of that salt at that temperature, 25 degrees. Let's look at this one. It was a little different. We have a slightly more complicated KSP, but still we can just go straight into our change if you like here, because nothing really changes. This changes by X, except there's a 3 in front, so it changes by 3X, and this changes by 2X. And so now we can write our KSP expression, which we did before. So there's our KSP, and now we just substitute. So 7.9 times 10 to the minus 18 equals 3x cubed times 2x squared. Well, that equals 27x cubed multiplied by 4x squared, which equals 108x to the 6th. So 7.9 times 10 to the minus 18 equals 108x to the 6th. So just notice when you have a more complicated KSP expression, more complicated x values, you get a slightly more complicated x to solve for. But that said, x is still solvable. So you just divide by 108 and then take the 6th root, and you get 4.4 times 10 to the minus 8 moles per liter. So solubility of lead 2 phosphate is 4.4 times 10 to the minus 8 moles per liter. So again, what is the molar solubility? It's telling us essentially that a saturated solution would be arrived at by making up a solution that's has a concentration of 4.8 times 10 to the minus 8 moles per liter at 25 degrees Celsius. Now, just one thing to point out, be careful when you are doing this. So again, the phosphate ion concentration changed by the variable 2x, so make sure you write 2x bracket squared, because that's what equals 4x squared. If you forgot to put the brackets around there, you might leave it as 2x squared, and you would end up determining the wrong molar solubility. So just a little word of caution. Be careful with those brackets. Make sure they're there to guide you. Okay, so next thing we want to be able to do is calculate a KSP. So we're going to calculate the KSP of calcium fluoride given that its molar solubility is 2.14 times 10 to the negative 4 moles per liter. So first thing, write a dissociation equation. So there's our dissociation equation from our previous example. So calcium fluoride solid dissociates into 1 mole of calcium 2 plus ions and 2 moles of fluoride ions. KSP expression is going to look like that. Concentration of calcium ions multiplied by the concentration of fluoride ions squared. And so after that, all we worry about is we're going to substitute our variable x, but we know what x is. X equals 2.14 times 10 to the negative 4. There's a single x for calcium, so that's going to be 2.14 times 10 to the minus 4. But there's going to be 2 times x for fluoride because it's 2F minus, because it's going to be 2 times 2.14 times 10 to the minus 4, and that's all squared. And so when we plug away at that, we get a KSP for calcium fluoride of 3.92 times 10 to the negative 11. So the KSP of calcium fluoride at this temperature, which isn't stated, 3.92 times 10 to the negative 11. All right, one more example. So here's a little more complicated one. Calculate the KSP of cerium iodate, CeIO34, given its molar solubility of 1.8 times 10 to the negative 4. So again, same idea. We're going to write a dissociation expression. So cerium iodate solid yields. This is a 4 plus ion, cerium 4 plus 4 times the iodate ion, IO3 minus. So there's a dissociation equation. And again, so here, if you wanted the values of x, the equilibrium concentrations for this cerium iodate, well, they're equal to x. There's 1 mole of cerium ions when it dissociates, but there's 4 moles of iodate ions. So this is how you're arriving at those values to substitute into a KSP expression. KSP equals cerium 4 plus concentration multiplied by the iodate ion concentration brought to the power of 4. Substitute 1.80 times 10 to the negative 4 times 4 times 1.80 times 10 to the negative 4 raised to the power of 4. And so when we put that into our calculator, we get 4.84 times 10 to the negative 17. So the KSP of cerium iodate at this temperature is 4.84 times 10 to the negative 17. And so again, that would indicate the equilibrium lies far to the right or far to the left. And based on the concentration of ions in solution, that seems to be borne out. Pretty low concentrations. So KSP and solubility product equilibria. So that's the quick view on that. Don't forget, write a dissociation expression to get your heterogeneous equilibria. KSP then is a single line only. It's the products on top. And then solving, either calculate a molar solubility given the KSP or calculate a KSP given the molar solubility. So that concludes this video.